I will record this video. I think it's working. Okay. And model wizard. It's a two-dimensional model, and laminar flow. Double click or click add, both okay. And study, okay. It's the same as last time, but in the study part, since we are gonna analyze some changes in the flow field, we choose time dependent. Double click to create a new study. Okay, everyone followed me to this part? Well, okay. I'll wait for everyone finish the opening. Okay. Oh, yeah, it's recording. So when you are opening your software, I'm gonna give a brief look through of this topic. As you can see, um, these pictures are showing what is are showing slow flow through over a slow flow over some solid things like cylinder or a plane or a wing, something like that. And the flow is steady and constant. As you can see, those flow after those solid is very steady and smooth, namely. But if the speed, if the velocity of flow is relatively large, you will see the flow separates at some point of the solid part and shed some eddies after the flow goes over goes behind the solid part, and for this time we are gonna analyze the eddies called Karman vortex street. That is eddies shedded behind a cylinder in a fluid flow field, and those are different. Those are common vortex streets after different with different flow velocity. As you can see, the Reynolds number of 100 and a different other speed. And the random number is defined as the inertial forces over the viscous forces. That is, rho is the density of fluid, and in our case is water, and the U is the flow speed of the free stream, which means which means the flow of which means the flow that is the ball, which means the flow, the speed of fluid not close to the wall, okay, and d is the diameter of the cylinder. You can see that the flow, when the flow goes over this this cylinder, it will move across this cylinder, and the diameter of this cylinder is a critical parameter of this flow, and the mu is the dynamic viscosity of the fluid. It will have influence on the fraction and other forces of the flow. And after that, there are two forces that we care most about, the drag forces and the lift forces. As we know that a plane or something like that, there are three main forces. There are three main forces. Excuse me. There are three main forces in the analysis of plane. The gravity, G, and the drag forces, and the lift. And if a plane or something like that would fly, or if a vehicle like automobile, when an automobile is driving on in the air, those forces are the main forces that have influence on maybe the oil using, or the speed or something. And the gravity is, if we see it as a constant, the lift forces and the drag forces are what the what our shape, what the shape of this thing we are studying mostly controls. So we will analyze the drag forces and lift forces, and the drag coordinate and lift coordinate, those forces, and those dimensionless number defined with drag and lift. And after that, there is a frequency of vortex shedding there is a frequency of vortex shedding that Karman vortex street. The Karman vortex street is predictable with the frequency. The eddy, as you can see, the eddy will shed each in turn of both sides of the cylinder, and the frequency of this procedure of this process, the frequency of this process is predictable and calculational. So we will talk about the frequency at the end of this. Okay. Have you all have your software all open? I will go around to make this. Okay. So the routine, the model wizard routine. Click model wizard to create a new model, and we choose two-dimensional model this time, and move down to fluid flow. It's the same as last time. Okay, and single phase flow, laminar flow. Double click or add, both okay. And study. Everything is the same as last time, but when we select study, since we should analyze the change of flow and the vortex shedding, we are gonna choose time dependent study. Double click to create our new model. Is everyone following me? Anyone have questions?
Hello, Prof. Please, you said after choosing 2D, we select what?
What? Pardon me?
Is after selecting how do we select the laminar flow?
In fluid flow, you move down to expand the list of fluid flow, and there is a single phase flow. You expand the list of single phase flow, and you will find laminar flow. Okay. I'll show you this. Here, add physics, and here it is. Fluid flow. in the list, and the first single phase flow, laminar flow. Okay, am I making it clear? Hello, Usu? Am I making it clear? Can we go to the next step?
Please, it's clear.
Okay. And we should make next. We are moving to the geometry part. We will build a geometry in the two-dimensional axes, two-dimensional. And first we will make the fluid field. We create a rectangle by right-clicking the geometry, and you move down, you can find rectangle. We define the width. The width should be, let me see.
Excuse me, Prof.
Say? What's your question?
Please, yes, please. After adding, selecting the laminar flow and adding, can we start from that side, please?
You will come to a study. You should add a time-dependent study. Okay? Just double-click it. It's okay. Can we move on? Also, or oh, sorry. It's 0.41. Ah, that's correct. And we define the width and height, 2.2 meters and 0.41 meters. Can we move on, everyone?
Prof.
Okay.
Excuse me, Prof.
Okay.
Yes, please. After selecting the time dependent.
Yeah, you should.
Yes.
Yeah, you say?
I think my internet is quite slow because it seems there's always a delay in seeing and then the action being performed. So like after time dependent, selecting time dependent and steady, if we can start from that side.
You should right click geometry 1. Can you see that? and right click it and move down to find rectangle. You create a rectangle in your geometry, in your graphics. And you will find size and shape in settings, and input the width and height, of the rectangle. Okay. Don't worry. I am recording this. I am recording this lecture, and I will put it on YouTube after class. Okay. So don't worry. You can have it. You can watch it after class or anytime you want. So I will. So have you followed to this step, to the width and height?
No, please, because in my settings I have geometry 1. It's depicting geometry 1.
Yeah, geometry 1, and you right click geometry 1 in the list, in the model builder list, and move down to see rectangle. Okay.
I've seen rectangle.
Yeah, you left clicked to create a rectangle in your model builder. Okay.
Okay, done.
And you right click to select this rectangle 1 you have just built. You will see size and shape. In the size and shape, you can define your width and height as 2.2 meters and 0.41 meters. Okay. And the position you could leave it 0, 0. Don't change it. Okay, everyone. All right. And the next step, we will build a cylinder in this part, in the flow field. Right click the geometry 1, and there is a circle in the list. You left click it to build a circle in your model. And the radius, we define it 0.05 meters, and the center is 0.2 and 0.2. Oh, sorry, 0.2. And build. Okay, everyone. All right. And as you can see in this, as you can see in the graphics, in the geometry is both gray. The circle and the rectangle are both gray. Um, we should make this circle a solid, but not fluid. So we will cut the circle from the rectangle. We use we right click the geometry to booleans and partition.
Excuse me, Prof.
Yeah.
Please, at circle 1, after inputting the radius 0.05 and then the center, the x and y values, what should I do to include the circle?
0.2. I have zoomed to that part. Okay. Can we move on?
Prof, please, what I mean is my circle is not included on my rectangle. So how do I get it included on the rectangle?
What do you mean included?
Just build model. Click on build model. If or build selected. Sorry.
Yep. You build selected, and your graphics is not look the same as mine, or what? What is the?
Yeah, it's now okay. I didn't see the build selected. It's now okay. Thank you.
Okay. And next step, right click geometry 1, and move down to booleans and partitions, and difference. That means it will leave. It will cut the same part of the two geometries and leave the difference. You can see difference. There are two selective part. First is object to add. We choose the rectangle, and we subtract the circle from the rectangle. Build selected. You will find the rectangle has a hole in it, and if we set the rectangle fluid like water, the hole inside the fluid field can be seen as a solid, or as solid, and if we define the rim of the circle a wall, and it will be a wall between the not between in the fluid field. So after making a difference, have you all made that difference? Just subtract the circle from the rectangle. What about everyone else? Will you follow me to this step? Shall we move on? What about Usu, Mona, and
Prof, please, with the object to subtract.
yeah?
I can't get the C1 in it.
Why can't you? You should click on the switch to turn on selection, to activate selection, and you can choose, you can select. Okay. Have a try.
Okay, done. Please.
Okay. So I will move on. You build all, in case you didn't build it. Last time we used the material from comsol library, but this time we will try to define a fluid by ourselves. So we right-click materials and move down to blank material, and you will find a blank material in your settings part, and we we use water as no and the material is it's not water, it's it is a personal defined material. Set the density 1 kilogram per cube meters, and the viscosity, the dynamic viscosity as 1/1000 Pascal second. Okay. You can also define it in the basic. So do you have any questions of this creating materials? And
Well, actually,
okay.
I couldn't
Please.
find the basic in my model builder. I only have material one, but I didn't find basic.
You click on the small triangle of
Oh, okay,
okay.
okay.
Both is okay. In the basic, this part is that you can have more detailed settings and add some other quantity of that fluid. As you can see, if you click the plus icon in the basic settings, you will find the window pop out, and you can select many other options of fluid properties, but these are not what we are discussing today. Just in case you need it, it is needed. I tell you this. Okay. So have everyone finished this material adding? All right. And we will move to the physics setting in the next step. And in the laminar flow, we choose the wall. As you can see, it is the wall is all the boundaries are selected as wall, but we should make the flow move in, flow in this fluid field in this part, and flow out of the fluid field in this boundary. So we right-click to add an inlet of the flow, and choose the leftmost boundary as inlet, and the velocity we can use fully developed flow as what we used last time. We define it 1 meter per second, and outlet, we choose the rightmost boundary as outlet, and you see now the boundary, the wall is defined as the inner circle and the two up and down boundaries as wall.
Excuse me, Prof.
Yeah.
Please, how do we get the inlet
You right click.
and the outlet?
You right click the laminar flow, and in the list given, you will find inlet and outlet.
Launching, please, the outlet, we didn't select any condition, whether pressure or velocity or anything. We didn't select anything. Why is it so?
Because we just need to define what goes in our fluid field, and what we are studying is the fluid field, is inside the fluid field, and the outlet, it means that the fluid is flowing out of our study, is like you have something like a washing machine, and you put your clothes in the washing machine, and the washing machine works. What you want is the working in your washing machine, but not those waters after the washing machine wash your clothes. So we don't need to define the outlet. Okay, we just define the inlet to make sure that water goes in our washing machine. And
Thank you, Launching.
yeah, okay. And we can move to the mesh part. We wait a sec. We make a free scored. Right click and make a free chord mesh, and move down to size, and you click Fine to build all. You will see it. It is not so fine because it is general physics. So wait a sec. Let me see. Finer. That's not so fine. So you select fluid dynamics and build all. You'll see the fluid. Physics controlled. Please wait. Yeah, physics controlled. And finer. Beautiful. That's better. You click mesh. Don't need to create anything in the mesh. And in the sequence type, you choose physics controlled mesh. And in the element size, you choose finer. It means your element size, your mesh size will be relatively small, and the physics controlled. The comsol your software will automatically set your boundary layers some more fine, and in free flow, the mesh will be will be larger, and so the calculations near to the boundary will be more accurate, and at the same time, your computation time will be relatively short. Okay. So have you all made your have you all built your mesh?
Prof, yes, Prof, I've built the mesh, but look at the
Excuse me?
outlet and the laminar flow. Mine, there is caution sign there.
Pardon me? You have your microphone echo. You have echo in your microphone. Can you pardon me? Can you repeat your question?
Thank you, Prof. Please, what I'm saying is that under the mesh, if you go under the flow, under model builder, my outlet, there is caution sign there.
What? Your outlet?
Yes, please. There is caution sign there. It seems we didn't choose anything on the outlet.
What did your model builder say? What is the caution?
Because I'm screenshotting and then
sending
it to.
Okay.
Yeah.
So what is the caution? You didn't select your outlet. You should select the rightmost boundary as your outlet. That caution means that you didn't have any boundary selected as your outlet after you create it. Okay, you just select this part as your your outlet, and that caution will disappear. Okay.
Yes, please. It has disappeared.
Okay.
Yes, it has disappeared. Thank you.
Have you finished your mesh? Have you finished creating your building your mesh, Mr. Wusu?
Yes, please. I have
Okay.
finished.
Okay. And let's go to the study part. We should show the show default solver in the study 1. It's the same as what we have done last time in the last lecture. You just right click the study 1 and move down to please wait. Move down to excuse me. Move down to show default solver, and you left click to select step 1, time dependent, and you should oh wait, solution 1, time dependent solver, and in times typing, and there is a time step constraint. Please wait. Let me see. I'm stepping. Taken by the solver and forget it. We just define the times, the times that the times taken by the solver. But let me see what the what the application gives. Yeah. the range the times you first you delete you can delete the time set comsol preset for you, and you move to the to click this icon. What should we call this icon? The range icon, maybe. To the range icon, and there will be a window will pop out to help you input your start, step, and stop. Start and stop means the first and the last steps shown in the result, and the step is how long your time step, how long between two steps of your result, and as is instructed, the start will be 0, and the step is 0.2, and the stop is 3.4, and you add it into your times into the times bar, and you can add another range of times into the seven. Okay. 0.02 and 3.5, and the step is 0.02, and the last step is 7 seconds, and you click add to add 2 ranges of time into your study. And the why should we add 2 ranges of time into this study? In the first stages, you can see the step is relatively long. That means in the first in the early part of your calculations, the flow is not steady. So you should have some time to you should let the software some time to make the flow steady. But those results we don't care about it, so we can have we can let it rather long steps to let it pass quickly, to resolve calculational resources, to reduce calculation time, and in later part, when the flow is more steady, and in those parts we will analyze the flow, so the steps are rather small, and we can study on the flow more carefully and more specific, more accurately. So I have pressed on my space bar accidentally. Now we can try to let the computer calculate. This could take some time. Hello, Noor. You are late for an hour. Congratulations. I shared it. Please. Thank you, Mona. It's okay. It's okay. I have recorded the full lecture. I'm recording it. I think I'm recording it. Yeah, I'm recording it. And I will upload it to YouTube after class. So you can watch it after class, and the lecture has been has started for an hour. I can't go around. I can't go back to the first step to let everyone to make everyone watch it again. You can go. Okay. Actually, I'm not the professor of this course. I'm just assisting my my boss to give you lectures. So you don't need my mail or WeChat. Okay. I'm just giving the lectures. Okay. Thank you for cooperation. And if everything goes right, you will get this after your calculate. Um, we will get excuse me. you you will get this after calculation, and as you can see, at first the velocity field is like blank. The velocity is 0 everywhere, and at what the problem? Okay, and at the next step, you will find it. Hey. Looks better. And by each step, you will find that the first flow is moving through the flow field. Hey. And after some time, the flow will become constant, and by constant, I don't mean the flow is steady, but the shedding of those eddies is of a steady frequency. Okay, and do I need to wait for your do I need to wait for you to finish? Mr. Wusu, you didn't you must haven't set your inlet velocity. Okay, I will wait for you. But it may take a long time. So you should be you should be prepared. Mr. Wusu, you should set your velocity of inlet, because if you don't set your inlet velocity, there will be no flow. There will be the water in your flow field will be calm as nothing. Okay. So you just set your inlet. You just give your inlet a boundary condition as fully developed, and average velocity as 1. Okay.
Please, I'm under boundary condition. I'm not seeing the fully developed option for me to choose.
The last one should be fully developed. Why isn't?
Okay, Prof, please, I've seen it and I've selected it.
Okay, and you should set the average velocity as 1 or anything you like. Just don't too small and don't too big. Okay. Something like
Okay.
1, 2, 3, 4, 5 is all okay, but not 100 or 1,000.
Okay.
Okay.
Okay. Okay, I've done that, please.
Okay, and you can move to study and let your computer start to compute. Magnifier. So I will pause. Go. Okay. And as you can see, the velocity field of this thing, and we will try to add some other things to this velocity field. You right click the you right click the velocity SPF and move up to more plots, and carefully to the bottom there is a particle tracing with mass. And those things comsol have preset for you. Just leave them alone and don't bother them. You move to the mass, and hey, my mouse is out of control. To the mass, and set it as 4 times pi over 3 times 1e minus 9. Excuse me, minus 9. that means 4 pi over 3. That is the volume of a ball, a sphere. You can see the volume of a sphere. Sorry, sphere. The volume of a sphere is 4 over 3 times pi r cubed. So that is a mass of a sphere, which with the radius of 1 millimeter. Okay, and the x component of initial velocity is u, and y is v. In comsol, u means the x component of velocity, and v of y, and w for three-dimensional is the z component of velocity, but we don't use it since we are using a two-dimensional model. And move down to particle positioning. The particle conditioning is x is 0, and y should be a range of it starts from point 1 to with the step of 0.05 and stop at 0.3, and we add it. That is in the inlet. We add several points from point 1, point 15, point 2, 0.25, 0.3. We will add five particle tracing from the inlet, and those particles will move together with the fluid, and it will show you how the fluid flow in the flow field. And we move next to release, and we will release particles for several times. So we choose at intervals. At intervals, it means that you give a start time, and you give the time steps, and it will release for several times since your start time, and every time step it will release particles in your selected in the time in the positions you have set. So we choose start time as like 3.6 seconds. Since we have set our range of exact accurate calculations as 3.5, so we just release our particles at 3.6 seconds, and the time between releases we can set as 0.4 seconds. That means the comsol will release particles, release those 5 particles every 0.4 seconds. And we choose coloring and styles. As you can see, there are lines in the flow field but that's not very that looks not very good, so we just give it none and plot it, and those ugly lines will disappear, and what we want are a point that we can see in the flow field. And now you can see there are several red dots in the flow field. But you can see the particles you set are sticking to the outlet, but that's not what we want. So we choose stick to boundary, change it to disappear, and we plot it. Now they all disappeared, and now it looks better. Excuse me. And now when we look at the flow field, you can see that when particles are released, you can see the red dots moving with your flow, with your fluid, and watch them go with the motion of the eddies, and in many other cases, you can also use this technique to capture or to catch the motion of flow in your flow field. And as we have mentioned that in mentioned at the beginning of this lecture, we need to what we care about is the drag forces and the lift forces of the flow of the to the cylinder. So we will calculate those forces. Right click on datasets. I should zoom in. Right click on the dataset. Have you followed me with the particle tracing part? All right.
Yes,
Okay.
but the part where you did the animation, that was where I couldn't get, but I was following.
Okay. So in the next step, I will introduce you to the to some calculations of forces in the in the flow field. You right click datasets, and in more two-dimensional datasets, you can find excuse me, in more datasets, you will find integral. That is the integral with in the flow field that comsol will automatically compute for you, and you can use it to calculate forces or maybe the pressure or something or some other thing other quantities. And in derivative value, no, you right click on results to create a one-dimensional plot group, and in the settings, you change the data set to integral 1, and you right click in the list in the model builder list in the one-dimensional plot group 3 to add a point graph. Yeah, point graph. And in expression, you should insert minus REAC F V. There's no plot it. as you can see, the receive function in comsol, it is a integral function of comsol to calculate force, and v means the velocity in y axis, in y direction. And if you give a and if you
I couldn't get your graph. I'm getting my graph is empty. I don't know why.
your graph is empty. Did you set your data set as integral 1?
Yes, I did.
How could it be? It shouldn't be. Can you screenshot your settings of point graph 1, and I will try to figure it out. It is connected with the previous fluid flow. The actually, this means this represents the lift forces. Take automatically from previous flow. Yeah, integral is right. Can you screenshot your point graph 1? What do you mean null? What do you mean null? What do you mean by why don't it take automatically from previous fluid flow data?
Professor, you were showing fluid flow before this graph in which we inserted some particles in the fluid to observe their movement. So isn't this graph related with that?
No.
What this function is telling us, I'm not getting it.
The particles. I think maybe you're asking about those particles we are adding, and the
Yeah, this
um,
thing. The
there.
graph is not related with this motion.
Yeah. The graphic, the graphics, the graphic we just plotted this graphic have nothing to do with those particles. The graphic is the forces that the walls, you know, the walls. Can you see the blue parts, the blue boundaries?
Yes, I can.
What we have just calculated is the forces that is
Acting on the walls.
yeah, that is acting on the walls, and
Okay.
and this V means it is on the direction of y-axis. I think it means that. And the particles, those particles are used to illustrate the flow of the
Direction of
fluid.
flow. Yeah.
Yeah, and
Okay.
it has nothing to do with the forces. Okay. Mr. Adi, you have missed a C. You have missed a C in the expression. It is REACF. REACF.
I just put the C there, but still it's not working. It's an empty graph.
Huh? I can't hear you clear.
I have inserted it. I have inserted a C, but it's still not working.
Why? It shouldn't be. Can you screenshot it for me?
Okay, right away. I've done it. I'm sending it.
Okay. It shouldn't be. Have you clicked plot?
Yes, I have.
The time selection. You should select all time. You have put it on manual. And
Okay.
I recommend you just set the data set to parent. Okay. It will automatically fit the data set to its parent. As you can see, parent, son. The parent is one-dimensional plot group 3, and the point paragraph 1 is the child is the son of it. So you just set it as parent, data set as parent. It's okay. It will automatically
Yeah,
okay.
yeah, it has worked now.
Okay. And as you can see in this PowerPoint, the lift coordinate is defined as 2 times the lift force over rho u to the power of 2 and the projected area. So if we put the if we put the if we put the function in the expression part, we will get the excuse me. We will get the lift coordinate. We will get the graphic of the lift coordinate. Let me put it in.
Please, Prof, can you zoom it so that we can see it clearly?
Please wait. Wait. I haven't finished it. 2 times.
Prof, please, it is now that mine has finished and I got the shape as you had.
What?
Yes, I said that I now have the shape as you got. It's not that my computer has finished with the results.
Oh, you have finished. Okay. So please wait. Please wait for a second, and I will finish this. Equals.
Yes, please, you continue. Once you post the video for us later on, I will continue from where I reached.
Yeah, okay. I'm recording it, and it will be uploaded right after the lecture is over. 0.05. I know. 0.05 meters. I think this should work. Yeah. In comsol, you can click this icon, this show more options icon in at the top of your model builder to show more to show more options with this icon, and you can tick the equation view to show equations in your model builder, as you can see this. And in the equation view, you can check those variables that is used in the comsol calculations, like the SPF rho represents the density of your domain. You can see, and you can pick those variables out to to do your calculations. As you can see in this case, we pick the SPF row out to in this function. And also you can set it as what you like, because actually the material is defined. We define the material ourselves, so we can either use what is given as a variable, or just give a number to comsol. And if you use the number, you shouldn't forget the unit, or the unit will be rather strange. It is strange now. And as we can, next we will see the frequency of the eddy, the frequency of the eddy shedding. The Strohal number is defined as this, and if the Reynolds number is relatively large, this part will be 0, and this part will be very close to 1, and the Strohal number, you can just see it as 0.2. So the frequency could be approximately equal to 0.2 times the speed of flow over the diameter of the cylinder. So in this case, the speed is 1 meter per second, and the diameter is 0.05 meters times 2. It's 0.1, and there's 0.2. So the frequency should be 2 seconds. I think it's 2 seconds. So in the velocity, you can see the frequency. You can check the frequency, like in the you can see in the at 3.78 seconds. This edge is leaving the cylinder, and in the next, hey. Well, and in 0.2 seconds, another eddy is leaving on the other side of this cylinder. So the frequency is working. I think it's working. So I think that's all for today, and I will cut. I will make the recording and upload it